So now I want to talk about the function of myelin. I've talked a little bit about it. So myelin is that fatty sheath that's produced by either your oligodendrocytes and the central nervous system or the neural hemocytes or Schwann cells and the peripheral nervous system. And what they do is they wrap this fatty material around the neuron, and it basically insulates the neuron and allows for an action potential to move faster. So let's look at what that looks like. Here we have a neuron. This is my drawing, of course, of a neuron. And here's that same neuron, but now we have these little myelin sheaths. So if we have an action potential moving along an entire neuron without the myelin, then you're basically walking along this neuron. And I mean, these action potentials are quick, but when it moves all the way from, say, your central nervous system, the motor cortex, all the way to your gastrocnemius muscle to help you walk, that's going to take a long time if it's moving along the entire neuron length. Whereas if instead you have an action potential moving, but it can move from here and then just jumps to here and moves along this little spot and jumps here and moves along this spot and then jumps here to get to the end, that's going to be a lot quicker. And so this is called saltatory propagation, movement of the action potential between the myelin sheaths through those nodes of reindeer. So action potentials propagate much faster down myelinated axons than unmyelinated. So myelin is a really important structure, and without it, a lot of problems can occur. So one disorder associated with degeneration of myelin is multiple sclerosis. So this is degeneration of the myelin in the CNS. This is an autoimmune disorder, and in this case, immune system cells are attacking the myelin sheath itself. So the information is going to move slower to or from our cerebrum to the different regions of our body, or from our autonomic nervous system to the different regions of our body, like through the thalamus. And that's going to cause problems, including muscle weakness, inability to move the way we want to. It's going to cause behavioral issues because now we're going to become depressed. So there's a lot of problems with this disorder. Guillain-Barré disease is a demyelination of the peripheral nervous system. So this is usually associated with some disorder occurring, and it just comes on very rapidly. So so this disorder comes on very rapidly, and it affects PNS systems. It's going to cause problems with blood pressure, with heart rate, breathing rate. That's an autonomic activity. And the difference between this and your multiple sclerosis is in this disorder, it usually almost everybody recovers. Whereas in multiple sclerosis, you have periods where there is no problems, where you're having no problems, and then the immune system starts attacking again. In this disorder, when it occurs, it usually lasts for weeks and then it goes away. And they're not 100% sure what causes this disorder. But it can eventually reverse itself, so it doesn't cause as many problems. All right, so now let's look at the actual plasma membrane of a neuron. So the plasma membrane of a neuron looks similar to most other cells. It has the phospholipid bilayer, and you have those proteins just like we have in all of our cells. Some of these channels, these protein channels, are pores that allow ions to travel directly through, while others are going to be receptors for specific neurotransmitters or specific other molecules. Some of the protein channels are going to be closed, and they'll only open when the cell membrane gets stimulated. And so acetylcholine can stimulate that cell membrane, and that causes these channels to open, and the channels, when they open, allow for ions to pass across. And so we have ligand-gated, and then we have mechanically gated channels. A ligand-gated channel is going to have some type of a area for a receptor to bind that activates the cell protein. Mechanically gated, when the membrane has been activated, it causes that protein to open up. And so this is like a little door, and it opens and then allows ions to move across. Voltage-gated channels, when an action potential actually occurs, or when sodium channels open and sodium rushes in, it changes the voltage. That can open up voltage-gated channels. Leak channels are always open, so then ions just can move back and forth at any time. So let's look at what an action potential is. To know an action potential, we first want to understand what a membrane potential is. And so a membrane potential is just the separation between the charges on the outside of the cell and the inside. And we learned this by taking tiny little electrodes and measuring the difference in charge inside and outside of that plasma membrane. So the outside is more positively charged, the inside is more negatively charged. The positive charges come from sodium, whereas we have an abundance of sodium outside of the cell. Inside we have lots of negative proteins, so charged proteins that are negatively charged. We also have different ions. Inside we also have some potassium, but the amount of potassium does not make up for the large proteins that are inside. So the inside is typically more negatively charged, the outside is positive. I talked about these channels already, but we do have lots of different types of channels, protein channels. Some of these channels are permeable to potassium ions. Some of these are gated channels, and gated channels are closed unless the voltage changes. And so here we see your permeable to potassium ion channel. So these channels are open and potassium can move in and out relatively easily, whereas sodium gated channels and potassium gated channels are always closed unless something stimulates the cell. So the neuron has a resting membrane potential of about negative 70 millivolts. So this is where the neuron sits at rest. And there's going to be small influxes of sodium coming in or potassium leaving, which is going to cause this resting membrane potential to change a little. It might become a little more positive. It might become a little more negative. So it's going to stay right around here. And again, we measure this using electrodes. So these are little tiny microelectrodes that attach to the plasma membrane, and we can measure the difference in the voltage. Threshold for a neuron is negative 55 millivolts. Threshold is where you have to reach for an action potential to occur. If you reach threshold, then you're going to have an action potential. Once you hit that negative 55 millivolts, enough sodium rushes in to cause it to move to here, an action potential will occur no matter what. You can't stop it once it starts. So this is called an all or nothing potential. If and only if you reach negative 55 millivolts will an action potential actually occur. So what is an action potential? Great question. That's a change in the polarity on the inside and outside of the cell. So the inside becomes more positively charged and the outside becomes more negatively charged. So this occurs because sodium channels sodium channels within the plasma membrane open and sodium rushes in. So the outside becomes more negative because that sodium is no longer outside. The inside is more positive because sodium does go inside. And that's what causes this change. There are 3 basic steps to an action potential. The first step is called depolarization. So depolarization occurs and sodium gated channels open and sodium rushes in. This brings about a positive, this changes the voltage on the membrane to a positive about 30 millivolts. Now, because all the sodium went in, the outside is more negative. And so this is what it looks like here. You have this -70, and then you hit threshold, and you have depolarization. Sodium-gated channels open, sodium rushes out. So when I think of sodium and potassium, I always think of 2 teenage kids, one that's lazy and one that's a little bit more outgoing and active. And so think of siblings, right, sitting on the couch. And someone someone knocks on the door. You have sodium that's really lazy, or that's really active, I'm sorry, not lazy, that's really active and immediately rushes to get the door. Potassium, on the other hand, is like, oh my God, someone came to the door, now I have to do something. So potassium is a little slower in moving, and potassium-gated channels are slower at moving. By the time sodium has already got to that door, potassium finally gets up and starts moving. And so the second step of the action potential is repolarization. The outside of the cell becomes more positive again because potassium rushes out. So not only do we have these sodium leak channels, but now our sodium gated channels open, and so potassium leak channels, but we also have these potassium gated channels that open and potassium rushes out, bringing back that normal resting membrane potential. And that's known as repolarization. So here, sodium-gated channels have opened, sodium rushes in, and then sodium channels close, potassium channels open a little slower, potassium rushes out, and this brings us back to that -70 millivoltage. And sometimes more potassium leaks out than sodium leaked in, and that causes a hyperpolarization. So at this point, if we were actually in class, I would ask, and I would wait for someone to realize what's going on. So I'm going to give you guys a moment to think about this. Can anyone see what's wrong? And obviously, you can't answer. You can answer, but I won't hear you since you're watching this somewhere else. But hopefully, you noticed, yes, we have positive charges on the outside. Yes, we have negative charges on the inside, but the ions differ. So potassium is an intracellular ion. Sodium is an extracellular ion. And so the third step of the action potential is to reconfigure, bring the cell back to its normal configuration. And we use sodium-potassium pumps to do this. Sodium-potassium pumps are active transport pumps that are found within the plasma membrane of the cell as well. And what they do is they pump sodium out and potassium back in. They're constantly working, so action potentials need energy because we're using energy to get these ions back to where they belong. If we don't do that, then the ions, if we keep sodium inside and potassium outside, what will happen is the next time we stimulate the cell, sodium-gated channels will open and sodium will move out, and that's going to hyperpolarize the cell versus depolarize the cell. So let's look at what a sodium-potassium pump how it works. So right now we have sodium on the inside, potassium on the outside. We have these sodium-potassium pumps that are constantly pumping sodium back out and potassium back in. First thing that happens is sodium can bind at that resting configuration inside the cell. When that happens, then ATP will bind to an ATP binding site. When ATP binds, the protein changes in configuration and opens to the extracellular region. So at that point, the 3 sodium ions can no longer bind, and so sodium is released. In this new configuration, though, potassium can actually bind. So potassium binds, 2 potassium bind, I should say, and the ATP hydrolyzes and so breaks down into ADP plus phosphate and releases, and when that happens, the sodium potassium pump goes back to its resting configuration, open to the inside of the cell. And then potassium can enter back into the cell. And so now we're open back inside the cell, so more sodium can bind, ATP can bind, sodium will release, potassium will bind, ATP unbinds, potassium comes in. So this just constantly is occurring to bring potassium back in and sodium out. And so here we have, and this is just showing the stages of the action potential. At this point here, we're just at rest. At any given time, we're going to have slight fluctuations from that resting membrane potential. But once a stimulus hits that causes us to reach threshold, then we're going to increase the amount of sodium inside of the cell to about positive 30, and then sodium channels close and the voltage will fall because potassium channels open and potassium rushes back in. And then we have that reconfiguration where we're going to bring about the normal configuration of the cell. Last thing I'm going to talk about in this video here are graded potentials. So I was talking about the fact that our resting membrane potential is -70, and there's always going to be some slight changes where you're going to have possibly sodium rushing in or potassium rushing out. So when small amounts of sodium rush in or potassium rushes out, anything like that, that changes the membrane potential either to a more positive number or a more negative number, but does not hit that threshold number. That's called a graded potential. So graded potentials are very small. They're short-lived, but they are additive. So you can add multiple graded potentials up until you hit an action potential. Graded potentials can be depolarizing, where you're increasing the positive ions inside of the cell, or hyperpolarizing, where you're decreasing the amount of positive ions or increasing the amount of negative ions inside of the cell. So an EPSP is an excitatory postsynaptic potential. So what happens there is you're increasing the amount of sodium in the cell, and this can move you towards a threshold. Whereas an IPSP, an inhibitory postsynaptic potential, causes hyperpolarization, so you're moving further and further away from that action potential or that threshold number. And so postsynaptic potentials can be additive, like I said, and eventually, if you have enough positive ions moving in through these dendrites, it can actually influence or cause an action potential to occur. So I'm going to stop here, and we'll talk about what happens at the synapse in the next video.